Bismillahirrahmanirrahim. Assalamu alaikum dear students. In today's video lecture we are going to talk about the importance of debugging in computer programs. To me, it is mandatory for every computer science student that he or she must master at least one good debugger. If you have not gone through my previous lecture of GCC, I will recommend that you should first go through with that lecture and then you should come back to this lecture, which will deal with the GDB debugger. In the first half of today's video lecture, I will talk about the basics of GDB, how we can load a process inside the GDB, how we can apply the breakpoints and watch points, how we can step inside our C code, how we can continue, how we can see the function calls, how we can see the values of different variables and how we can change them. This will be done with a bit of examples so that we should be able to find out bugs in the existing code. In the second half, I will be digging inside the GDB. We will be seeing assembly code inside GDB. We will be stepping through the assembly code. We will be seeing the registers which are available to us. We're going to change the values of those registers. We are also going to see how a code dump file is generated when a process is killed by the OS due to some signal, and I'm going to load that code dump file inside GDB and postmortem the dead process. Finally, I'm going to see how function calls are made in a C program and how function stack frames are pushed on the stack on each function call and how they are popped from the stack whenever a function returns. I will also touch upon the GUI mode, not exactly GUI mode, the N curses mode of GDB, which will be more interesting to those students who are used to using the GUI tools. I hope today's lecture will again be very informative for you. So although I'm very tired today, but let's start playing again. Who am I? I'm Arif. The name of my machine is Arif and present working directory is /home/Arif and GDB. Dear students, before start playing, let's talk a bit about theory. What is debugging? To me, debugging is the science and art of finding and eliminating bugs in a computer program. Well, to me it is both science and art. You may differ with me. There are a lot of debugging tools available in the market having both a command line as well as a GUI interface. While programming in C, C++, Objective-C and Objective-C++, you might have used different development environments like code blocks, Eclipse and Xcode. They all use GDB behind the curtain. In the simplest words, a debugger is a program running another program. Let's see what the main page of GDB says. It says, the purpose of a debugger such as GDB is to allow you to see what is going on inside another program while it executes, or what another program was doing at the moment it crashed. The plethora of information on this man page, you can go through it at your own time. Right now, let me do a hello world with GDB. First of all, let's see this basic hello world program, which simply says, welcome to the world of GDB. Let me compile this program. And let me execute it. Let me load this program in GDB. We can start GDB by simply writing GDB on the command prompt if it is installed. Once I give the GDB command to my shell, it searches for this command, loads it in memory and gives me a prompt. GDB is an interactive program. It is waiting for the commands from me to execute. Within the GDB, if I want to run shell commands, I need to proceed the shell command with a bank sign. For example, if I want to clear my screen, which is not a GDB command, which is a shell command, I need to proceed it with the bank sign. Okay, let me load this program in GDB. The command to load a program in GDB is file. This is a command of GDB which says this executable should be loaded inside GDB. Once I press enter, it says reading symbols from EX1, no debugging symbols found. Students, if you want to load a program file in GDB, you must give it a -G option before compiling. I mean to say, you should write something like this. This option -G basically instructs the compiler to keep the debugging symbol in the object file. For GDB in particular, you can say GDB over here as well to give the complete list of the required information in this exe file to be loaded in the GDB. So let's do it again. Run the GDB with the GDB command, load the executable with the file command, and this time you see reading symbols from EX1, done. Now the program is loaded in GDB. If we want to run this program, we give the run command. Once I give the run command, GDB says starting program blah 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 EX1. This is the output of our program, and this is an informative message given by GDB which says that process with the ID 28068 exited normally. What does this inferior one? We'll talk about it a little bit later. Now again we are on the GDB prompt. Remember students, the EX1 program is still loaded. I can still run it. And I can press Q to get out of the GDB. You can load the program EX1 by giving it as a command line argument to GDB. You see this line again? So there are two ways of loading a program in GDB. One is using the file command within the GDB, and the other is giving the executable name as a command line argument to GDB. And the output is the same. There is another way of loading a program inside the GDB, that is using the attach command. You write down attach over here and write down the PID of a process which is already running somewhere over here, and it will load it for you. Let's give it a try. This is the top program which is running over here. Let me load this program inside the GDB. For that, sorry for the typos, let me be root. Let me check the PID of the top command, 28100. I run the GDB. This -Q says that don't show that initial information which you give me about the ways to get help in GDB and its versioning numbers and so on. So now to load this program is I say attach 28100, and this is attached, and if I want to see the contents of the registers, let's suppose that top is using, I give the info registers command, and these all are displayed over here. But right now we are not going into the details of these registers. I will do it after about 10 or 15 minutes of today's lecture. So let me exit again and be Arif. and let me pass a kill signal to this stop as well, or control C signal. Control C gives the SIGINT signal to the foreground process. Okay, fine. Let me load this program again, EX1. So this program is loaded, and once this program terminates, it gives a message which is clear to us, but this inferior part is not very clear. So let's talk about what do we mean by this inferior. Dear students, GDB let you load multiple programs in a single session and switch focus between them. GDB do this with the help of objects inferior, inferior 1, inferior 2, inferior 3, and so on. Right now we have only one program loaded in GDB. I can get the info of that, info inferiors. I can load another program in GDB. Let's suppose there is a program, suppose EX2, and I say file, no, not with file. This time I have to use add inferior -exec EX2, and let me load another program EX3 as well. If I get information about programs, I see this. So right now inside GDB there are 3 programs, EX1, EX2, EX3. I don't know what are the contents of these executables, with the number of 1, 2, and 3. And right now the focus is on 1 because of this asterisk symbol. If I want to change focus, I can use again inferior command with number. Let's suppose it is 2. Switching to inferior 2. Now you see I have the focus on this program. So let's run this program and see what it do. I've run this program. It is asking for a number. Let's suppose I give 5. I press enter, and it prints PUC 85 times and says inferior to process 28173 exited normally. Gentlemen, we can load multiple programs in GDB, but right now I have executed them one by one. We can always execute them concurrently or maybe simultaneously depending on our machine. How to execute multiple programs simultaneously within a GDB session and let those programs communicate using different IPC mechanisms and do a lot of forks and maybe having multiple threads within a process. This inshallah will be done in some future video. Right now let me quit and let me tell you how we can get help within a GDB program. Dear students, to get help you just type help. Oops, but this has to be done of course within GDB. Let me run GDB in a quiet mode and type help. So you see list of classes of commands. GDB displays you more or less 12 different classes of commands. Breakpoints, data, files, running, stack, and so on. If you want to see what all commands are there within each class, you type help and give the name of that class, command class. The command class is breakpoints. Help breakpoints will display all the commands which are there in that class. For example, break. If I do this, help break. Now this is what is the help about a particular command. So break set breakpoint at a specified line or a function. So let me repeat. Help. Simply typing help and pressing enter shows you the different classes of commands. And if you give a class name after help, it will show you the commands within that class name, and if you give the command name after help, it will show you information about that command, how to use it. So let me clear. Remember, within the GDB prompt, if you want to execute a shell command, you need to precede it with a bang sign like I have done here, because clear is not a GDB command, it is a shell command, so it must be preceded with a bang sign. Dear students, we all have a fair idea, probably a fair idea of what are breakpoints. A breakpoint is a point inside your code where the execution of your program will stops whenever it will reach there. Every debugger allows you to set breakpoints, to disable them, to enable them, and to delete them. Soon we will see how we can do that. Other than breakpoints, we have watch points. A watch point can be set with the watch command followed by the expression. We can set a watch over a variable, for example number. On the contrary, a breakpoint normally stops at the execution of that program when execution of the program reaches that specific point. But over here, watch points, which are set with the watch command, they act on variables. Once you set a watch point on a variable with the command like, for example, watch space num, then whenever the value of this variable num changes, GDB interrupts the program and print out the old and the new value. Similarly, within the GDB, if you want to list the code, you can use the list command. For example, I have given the list command, but since there is no symbol table loaded right now, so it has not given me any output. So let me load some symbol table over here. I say quit. Let me load a code ex3 GDB ex3, and before loading it, let me do a cat of ex3.c. This is a program which receives a command line argument and convert it to integer and store it in a variable named num, and here is a loop. This program executes this loop that much number of times and displays PUCID. Okay, fine. I do GDB in quiet mode and load the program ex3, and then I apply a breakpoint with the break command, and I give the name of the function over here, and it sets breakpoint over there. If I do a listing, it shows me a list of the code that is being loaded in a GDB. Now if I press run is a command which starts executing your code. So once I start running my program, it stops at the breakpoint, which is at line number 6. You see here we have the line number 6. From here onward, we have various options. One is continue. Continue the execution of this program till the end or till the next breakpoint. So let's continue. We can type continue, or we can just press C, and we see we have a segmentation violation. Well, probably the issue is that we need to pass a command line argument to this program, which we haven't. So let me clear and let me quit and let me load this program again. Since this program needs to be given a command line argument, so I must give one. and that can be given with the run command. For example, let's suppose I give 5. So I give the command line argument of 5 to this program, which is passed to this, and this loop executes 5 times. You see? Let me apply a breakpoint now. Break at line number suppose 6, and let me run with the value of 3, and over here I continue now again, and you see it has continued, printed PUCID 3 times, and the program exited successfully. So students, we have seen how to apply breakpoints. We have seen how to continue from breakpoints. Let's see something more as well. The program is loaded. I just want to see is there any breakpoint enforced? Yes, there is, which has already been hit once. So let me delete this breakpoint. So to delete this breakpoint, the command of GDB is delete, and I need to give the number of the breakpoint. So there is no breakpoints or no watch points. So let me put a break again, break on main. Let me put a break again on line number, let's suppose 8. And if this is a multi-file program, I must mention the name of the file, colon, and then the line number. Now I see info break. So I come to know that there are 2 breakpoints, 2, 3. These are the logical addresses on which these breakpoints are held, and these are the actual line numbers of these source code files. We can always temporarily disable a breakpoint for the time being with the command of disable. Let's suppose I want to disable the breakpoint number 3. Now you see this breakpoint number 3 is disabled. Let me run the program again with the value of, let's suppose, 8. Let me make it 10. So let me check out what is there in num. So I use the print and I press enter. So there is nothing inside num right now. Let me use next. The next command to GDB says that execute next line as a single instruction. Even this instruction is a function, my GDB code will not enter into this function but will treat it as a single line of code. So now if I say print num, I will see the value which I have passed as a command line argument. This 10 will be there in num. Now this loop will run 10 times. If I want to run this program to completion, I can press continue. Otherwise I can press next again. And if I want to press next again, I just press N. And if I want to repeat the previous command, I do not enter anything and just press the key enter. So it will take the N command for me. So we'll see the value of variable I. It says that value of variable I right now is 2. If I want to change this value, I can change that. And if I want to display it in another format, I can also do that. /x means that display the value in hex format. O means display it in octal format. T for 2 means display it in binary format. And if I do not give anything, it will display the value as per the data type of this variable I. What is a command which can be used to check the data type of I, which is int. So let me change the value of I. I can always change it with the set command. I is equal to 6 or 5. Now if I say print I, it will contain 5. There is another syntax of changing the value of I, that is using a bracket and saying I is equal to 11. Now I contains 11. So once this loop will be executed again, this line number 7 will be executed again. 11 is less than num which contains 10. This loop will break. So let me do next. You see, we have reached 0, return 0 statement, and we're out. Over here, this is a different function which we have not seen in our code. Students, this is actually the function which is called by the loader, which is there in the standard C library, known as a special startup routine. This is the routine which is not written by you, but this is there in the standard C library in the file libc-start.c. Since this library is not compiled with debugging symbols, so that is why our code has not been able to enter into this library code. So it has shown this message to you. So please don't go into an idea that this is something an error. This is not an error. This is just saying that the GDB is trying to get inside that function. So we'll talk about function calling a little bit later, and you will understand what the function calling is. So let me quit GDB and let me say that what we have done is we have seen how to load programs in GDB. We have seen how to give command line arguments. We have seen how to apply breakpoints, get information about the breakpoints, the next step, and continue. We have got to know about inferior, how to get help. Now let's find out that how we can find out bugs in a program. Let's suppose we have a program ex4.c. This program basically asks the user to enter a number. The user enter a number, it is saved in this variable, and that the user gets the factorial after this loop, and that factorial value is displayed. Okay. So let me run this program ex4. It asked me for a number. I press 4. I know the factorial of 4 is 4 into 3 into 2 into 1, 24, but I get a 0. So that means there is a logical error in our code, which must be corrected. So let's load this program in GDB. I assume that this executable has already been created using the -g option. So the symbols are there, it's loaded. Let me list this code. Okay, let me put a breakpoint. Let me put a breakpoint at line number suppose 8, and let me now run the program. It will run till this line first, line number 7, and ask me for the number, and of course I will give 4. When I press enter, it will again move on to this line number 8, because we have placed breakpoint at line number 8, and it will halt over there. So now at this place, let me find out what is the value of different variables. If I say print, let's suppose I, so since this line is not executed, that's why this is showing me this. Let me say n. So now let me get the value of I. It is of course 0. It has to be 0. It is 0. It's fine. Let me print num, and to me num must contain 4, and there is 4 in it. Okay, fine. And let me print factorial. This is the third variable. So once I press enter, I get a garbage over here. So why it is so? Let me list the code again. Over here the factorial contains garbage. It is because that of course I have not initialized it. I just forgot to initialize it. So let me initialize it. Let me quit it. Let me open it in editor like Vim. I just want to open 4, and let me just write down is equal to 1 over here. Save and exit, and let me compile it ex4.c with the name of ex4. Let me say GDB in a quiet mode, load this program ex4. Okay, let me put a breakpoint again. Let me list it and see whether everything is going fine or not. We have to put a break at suppose line number 9. Well, let me run it. Once again I give 4. Now again let me check the values of various numbers. Print num, it contains 4 and it should contain 4. Print fact, it contains 1, and of course at this line it should contain 1. Print I, it contains 0. So I contains 0. Okay, so if I press N and see now, print I again contains 0 since it is not yet incremented, and you see fact is also 0. So I was containing 0, it multiplied with fact and changed the fact to 0. Now no matter how many times this loop executes, finally the factorial will be 0. So let me run this program to completion. The factorial of 4 is 0, which is of course wrong. So that means the problem is identified, and this time the bug that we detected is that we should initialize this variable I with 1 instead of 0. And once we have initialized it with 1, to ensure that the loop runs num number of times, we have to place an is equal to sign over here as well. So let's again compile this program and let's execute it over here, and this time it is working. Let me give 5. It's working. Let me give 10. It's working. Fine. So gentlemen, we have seen how we can load a program in GDB and find out what are the bugs in it, and of course after identifying them we correct them, and we again load the program and run that. Let me show you another program. Okay, we have seen it. Let me show you this program. Okay, if you see this program, it is very apparent that we are creating two variables I and j. J contains 0, and we are doing division by 0 error, and here we have the division by 0 error. So maybe once there is a huge program and the value of this j is computed somewhere else somehow, and then this line is being executed, it might be very hard to identify it. over here, since it is just 4 lines of code, so it is very apparent to identify this bug. But in a code of suppose 1000 lines, you may not be able to find this, and there are chances that this line might not work when you are testing the software. Once you have delivered the software to the client, only then this line gets executed, because it is somewhere in some if-else statement. So let me run this ex5. Once I run ex5, it says floating point exception core dumped. Students, whenever your process abnormally terminates on receipts of some signals like segmentation violation, floating point error, illegal instruction, or SIG-quit, Linux creates a core file which is the binary image of the program at the time of its death. So this program has died, ex5 has died. It should have created a core file in the present working directory, which is not there. If you do not see a file over there, probably you have set your u limit to 0. Set your u limit to unlimited and execute this command again, and this time you can see the core file is generated. Don't get yourself confused with this. By default this is set to 0, because if this is not set to 0, your system will keep on generating core files, and their size is quite a bit large, and they are in, let me see its size in KBs, 252K file size. So it's always better to keep it 0. So let me find out. This code is of thousands of lines, and let me find out where is the bug. So let me load this program in my GDB. I say GDB in quiet mode, the name of the executable, and the core file, and I press enter, and it loads this core file and just let me know what has happened and where. This is the logical address on which it has happened, and this is the line actually where it has happened, and this is the line. And now you have come to know that inside your code, which I assume is of thousands of lines, this is the line which we need to correct. So you see the power of GDB, how we can use these core dump files for the postmortem of our dead processes. The dead processes which have died due to certain receipt of signals. So, right, students. So let me switch gear and let's go into a little bit depth of GDB, and let's see what GDB can help us as far as the underlying assembly is concerned. So in the next 5 minutes or so, we are going to see how we can dive it into the assembly code of our programs using GDB. Let me load in quiet mode the very basic program of ours, that is the Hello World program in GDB. Let me list it for your comfort. This is a very basic program. Let me apply a break in main, and let me say it, apply break in the main function of this file. I assume that there can be more than one functions of the same name in different files. So anyway, main cannot be duplicated. So if I run it, it reaches that breakpoint. It says I'm going to execute now this line, but before it execute that line, let me use a command of GDB disassemble, and I give it the name of a function. Once I press enter, after giving the name of a function to the disassemble command, it dumped me the assembly of the main function. And over here this arrow shows that right now the instruction pointer is pointing on to this instruction inside the code section. If this assembly doesn't seem familiar to you, so let me tell you, this is AT&T assembly. You might be used to of working with the Intel assembly. So let me change the flavor of the assembly by the set disassemble flavor command to Intel. I can give over here ATT for AT&T assembly, which is right now over here, and I can use Intel to change the flavor of this disassemble, ASSEMBLE. So I don't know why this is not working. Set disassemble flavor Intel, and if let's suppose disassemble main, it's again the same. I don't know why it is so. So let me quit and let me come back again. Maybe I have forgotten an is equal to sign over here. Maybe. Isn't it? I don't know. Okay, forget it. We're not going into the detail of how this is working. Probably in some other lectures when we'll be talking about the NESM assembler, we will jump into this again. Right now we just want to disassemble, and we have successfully disassembled. If I want to see the source as well as the assembly at the same time, I can give the command disassemble /m main. Remember, over here I can give the name of the function, I can give the range of the source code lines, I can give the addresses as well. So to keep things simple, I use main over here, and now you see I've given this. So this is the dump, this is the push and the move function, how the main function is called. This is the printing of welcome to the hello world, and these two lines are basically the assembly of this. Return 0 is here, and finally we are calling leave and the return statement of the main and going back to that special startup routine. So dear students, this is how you see the assembly, and similarly you can see the values of various registers as well. Let me use info registers. So dear students, you can see over here 16 RAX, RBX, or R0, R1 to R15, 16 64-bit general purpose registers. Since this is a 32, this is not 32, this is a 64-bit architecture, so they are named as RAX, RBX. In 32-bit they are named as EAX, EBX, and they are 64, while in 32-bit architecture we have just 8 registers. Names of these registers for convention they are kept over here, otherwise you can also use R0, R1, R2, R3 and so on to this. These are the contents of these registers right now. This is a famous instruction pointer, RIP. You may be used to of EIP. This RIP, which is the instruction pointer which points to the next instruction to be executed. It's the flags register. The flag registers contains bits for different flags like the carry flag, the parity flag, zero flag, sign flag, overflow flag, and these are the 6 segment registers: code segment, stack segment, data segment, extra segment, and FS and GS also for extra segments. These all are the integer registers. If we want to see the other registers as well, we can use all registers. The all registers command show the initial registers up till GS. Then we have ST0 to ST7. We have about 8 80-bit registers, and then over have YMM0, YMM1, YMM2, and so on to YMM15. We have 16 256-bit registers for floating point values. So we have a lot of registers. Gentlemen, here I will particularly like to say something about this instruction pointer. This instruction pointer contains the address of the next instruction to be executed. Before a call, whenever you call a function, the value of this instruction pointer is pushed on the process stack. The control goes to the function executes, and once you return the instruction of leave, roll back the stack to the previous location, and this value, which is the return value, which is pushed inside the stack, is popped inside this register, and the control goes back to the caller. Soon we will see the stack of a process, and you will be able to understand it better. There is another important register that is to be mentioned over here is RBP. You might have heard it with the name of EBP. This is the base pointer. This base pointer always points to the bottom of the current stack frame. We will talk about stack frame soon. RSP, the stack pointer. This register always points to the top of the current stack frame. Last used or occupied address on the stack, not the next free available address after the top of the stack. Gentlemen, inshallah, some other time in some other videos when I will be talking about working with the assembly programming on Linux with NESM, I will give the details of these registers and how to use them, but right now we keep things simple. If you want to get the value of a particular register, you can use again the print statement, and if you want to see it in the hex format, you can say, let's put RAX. So no symbol in RAX. Let me list this, and info break. There are breakpoints. Let me run this from the beginning, yes. And now let me again info registers, and let me check the value of RAX. RAX is not in current context. I don't know. Well, let me run the program again. Let me show you this is important. GDB in quiet mode, EX, let's suppose 4, and info registers. No registers right now because it's not loaded yet. So let me apply a break in main. Let me run this program, and let me get info registers again. This time it will show me the registers. Previously the program was not loaded. So let me find out the value of RAX now. RAX is not in the current context, so let me run it again for a single line so that RAX come in context somewhere. Let me use some values. Let me put 4 and use next and next. Now probably RAX will be in context. RAX is not in context. Print /x RIP. So none of the registers is in context. Oops, I'm missing something over here. So gentlemen, whenever you want to access register, you must not forget to use a $sign over here. So let me do it like this. So it was not recognizing this variable RAX or symbol RAX, so I need to use a dollar over here. It contains 1. So I can always change the value of this variable inside the register by saying RAX, set RAX, let's suppose plus is equal to 9, and if I see the value again, it contains 10 and hex it's A. So gentlemen, we can step through the assembly using the step I command. We can use the next I command, and we can move inside the assembly, and we can play a lot. But right now I don't want to get inside the assembly. I just want to let you know how the stack works actually. So for the stack part, I've created another program that is stackdemo.c. Oops, it's a long program, but not tricky. So in this program, gentlemen, there are 4 functions. Stay with me. F1, F2, F3 and F4. F1 is a function which is passed a character pointer. F2 is passed 1 integer argument. F3 2 integer arguments, and F4 is passed none. The main function, it creates some variables, and basically it calls F1 with a character value. The function F1 creates some variables and call F2. F2 receives this argument in this variable and calls F3 with 2 values. F2 calls F3 with 2 arguments, A2 and B2, and F3 calls F4, and F4 calls return. F4 returns to F3, and F3 returns to F2, and F2 returns to, of course, F1, and F1 returns to main, and here it comes back. So let me repeat again. So we have 4 functions other than main. The main function calls F1, then F2, F2 calls F3, F3 calls F4, and we fall back in the same way, as we know that. The parameters of F1 are param1 underscore F1. The parameter of F2 are param1 F2. The parameter of F3 are param1 F3 and param2 F3, and F4 are not passed any parameters. F4 returns a value of 4 to F3, F3 returns a value of 3 to F2, F2 returns a value of 2 to F1, and F1 returns a value of 1 to main, and main returns, let's suppose, 54 to the one who called main. I hope the code is simple. You just need to understand that there are 5 functions including main. Main calls F1, F1 calls F2, F2 calls F3, F3 calls F4, F4 returns 4 to F3, F3 returns 3 to F2, F2 returns 2 to F1, F1 returns 1 to main, and main returns a variable M1 which contains 54 to its parent, which is of course a shell. Let me execute this program. I've already compiled it with symbols. It has executed and it has given the output. Well, that was really cool. It is not yet cool. It will become cool very soon. Now the value which the main function has returned, that is 54, has been received by the shell program, and you can access that value in a variable $?. Some of you might be knowing it because we have seen it in the bash shell programming portion. Now let me load this stack demo program inside my GDB quietly. Put me break in all the functions, main, F1, F2, F3, F4. Let me get information about breakpoints. So you see we have 5 different breakpoints. In main at line number 7, F1 17, F2 24, F3 31, F4 38. So when I run this program, it will first stop at line number 7, then if I continue it will stop at 17, then when I continue it will stop at 24, then when I will continue it will stop at 31, then when I will continue it will stop at 38, and then it will return in the same order back. I just want to show you how the stack grows and how the stack shrinks. So let me run. So right now, if I talk about the process stack, it contains one frame, that is a frame of the main function that is pushed inside it. Let me see a diagram for this. Yes, I have a diagram for this. Let me bring it close. Okay, so this I have shown you a portion of the process. This is a stack, entire stack, which grows from high address to the lower addresses. Remember, students, in Intel architecture the stack always grows down to the lower address. Right now the process stack contains one frame, that is the frame for the main function. And remember, the base pointer points to the base of this current frame and the stack pointer points to the top of this stack frame. There is a command named backtrace which tells you information about different stack frames. Right now it is saying that there is only one frame inside the stack having these arguments and maybe some local variables, of course. If I say continue now, I have stopped in function F1. Now if I see backtrace, we see there are two frames. There is a frame for the main function and there is a frame for the F1 function. So once the main function calls the F1 function, there is another frame over here. The RBP, which was pointing over here, is now pointing over here, and the stack top is pointing over here. The previous RBP is saved somewhere in this frame. The return address of this function, that is the next instruction to be executed by the main, is also stored in the stack. And then there are values for some local variables, and this RSP grows as the values inside this F1 are growing. It is using more and more variables and buffers over here. So if I press C again and C again and check the status of my stack frame, there are 4 stack frames inside my process stack. At the top I have F3, then F2, then F1, and then main, or vice versa. Main, then F1, then F2, then F3, and then finally of course F4. So let me go to F4 as well. I continue and I see backtrace. So now we have all the 5 functions. Let me show you your code from 1 to suppose 30th line. The main function has called f1. The f1 function has created some variables and called f2. The f2 function has created some variables and called f3. Let me list some more values. The f3 function has called f4, and here I am in f4. So now there are 5 frames inside the stack: f4, f3, f2, f1 and main. Now if I want to go back to the previous frame, there is a command named finish. Finish is a command that is going to execute this function, return the value of the previous function and stop over there. So remember, function f4 is going to return 4 to f3, called finish. Run till exit from number 0, that is this function. In f3 it has returned value of 4. Function f4 has returned 4 to f3. If I call finish again, function f3 has returned 3 to f2. If I see bt, so I have now 3 frames over here. The diagram might look something like this. Now we have 3 frames. We are in function f2. f2 is going to return 2 to f1. Finish. You see, now we are in function f1. Let me call bt. We are in function f1. f2 has returned 2 to f1. So f2 has returned 2 to f1. So once the process stack shrinks, this RBP moves back to this. This RBP gets the address of this location from somewhere over here. RSP moves back to here. RSP moves back to here because RBP is already pointing over here. We can always shift this RSP to here, and then this value is placed in RBP, and the return value we get, and we shift to this portion. So this is how we move back to the previous function. Let me finish again. So now we have only one stack frame available. Sorry. Now the situation is something like this. We have just one stack frame, one function frame inside our process stack. If I call finish again, finish is not meaningful in the outermost frame. In the leaf frame, once you are in the last frame, you don't call finish. You just continue from over there. So you need to press C so that the main frame goes back to another function, that is the C startup routine. So this was really cool. If you have understood this, that's great. If you haven't, you can rewind this part and see it again, because this is a portion which I'm going to hit again when I'm going to talk about the NASM in Linux. One last thing, gentlemen, that is the curses mode of GDB. We can run GDB in quiet mode and tell it to display me a bit of GUI using the libn curses. For this executable, -TUI, this option to GDB tells to load it in the curses format. So over here we have a panel above which shows the C source code, and over here we have a panel in which we can give the commands. we do have the option to see both the high-level language as well as the assembly language by saying layout split. Now you see we have the three panels. Above panel contains C code, then the assembly code, and then we have the commands. So if we run it, before running it, let me apply a break in the main function. And I put a break in the main function. You see something over here. This is pointing over here, and this in assembly. This is the current line which will be executed. Then I say run. The program has been started. The breakpoint is at line number 7 in the assembly code, and in the C code, and in the assembly code it is at address 4005A5. Now if you want to run it to completion, you can press N. Next, N will move to the next high level language code, and if I press NI or SI, it will move one line of code of assembly one at a time. So let me press N. So our control is over here and its assembly is over here. I press again N, you will see that I will move to probably some call function in the assembly code. Yes, so load effective address of this call, and then again say N, we have moved to the print statement, and over assembly over here I again just press enter, so it has executed and displayed. That was really cool. So I hope students you really have enjoyed all this. There might be some glitches in between. Please accept my apologies for that. Inshallah ta'ala, my next video on GDB behind the curtain is on the way. It will soon be unleashed, and in the next video lecture of GDB behind the curtain we will be covering that how we can use GDB inferior objects, how we can execute multiple programs in a single GDB session using them. We will see how to debug multi-threaded programs. We will learn debugging programs that make a lot of fork system calls to create child processes. We will also learn debugging programs that performs Unix IPC calls like pipes, FIFOs, message queues, and shared memory. And last but not the least, we will see how we can exploit this stack buffer overflow vulnerability of a program to create a backdoor in a remote system. Inshallah ta'ala, I am hopeful that within the next 2 or 3 weeks I will be able to prepare this video lecture as well, and by then hope you will enjoy learning and doing things with me in GDB. Last but not the least, gentlemen, I'm open for any suggestions. If you have, you can give in the comment box. You can always email me if you know me, arif@pucit.edu.pk. So I wish you all the best. Allah Hafiz.